Hello everyone, today we're going to be working on example 4-11 and this example is asking us to determine the resultant force and specify where it acts on the beam measured from A. So as you could see, we have our point A right here, and then from there we have three different type of loadings throughout this beam. For 1.5 meters, we have 6 kilonewtons per meter, then we change it to 9 kilonewtons per meter, and then we go back down to 3 kilonewtons per meter. So to determine that resultant force and to specify where the location is from point A, what I'm going to be doing first is I'm going to be finding first each of the forces for each of the different loadings, and then from there adding them together to find that resultant force. So this is going to be section 1 right here, this 1.5 meters. This is going to be section 2, the 3 meters, and this is going to be section 3, the 1.5 meters. So for R of 1, we have a span of 1.5 meters times the loading of 6 kilonewton per meters. For R of 2, we have a span of 3 meters times the loading of 9 kilonewton per meters. And for section 3, we have 1.5 meters times the loading of 3 kilonewton per meter. So for section 1, we should end up getting 9 kilonewtons. For section 2, we should get 27 kilonewtons. And for section 3, we should get 4.5 kilonewtons. So now to determine the location of these individual forces, we're going to be determining the location, since in the end, we're going to have to determine the location of that resultant force from point A, which is right here. When determining the location for each of these individual forces, we're also going to be determining their location from point A. So for this first section, well, to start off, since these are, I guess you could say, constant loading for each of these forces, and because of that, we know that each of those forces are going to be centered right in the middle. So it's going to be easy to determine that. What we could do is we could simply just divide each of these spans by 2 to get their location. But then when specifying their location, we're going to have to be doing it in terms of point A. So for this one, we can put that the location from point A is equal to 0.75 meters. For this force right here, for force of the section 2, we can put that the location is 1.5 meters. But for the section 3, the middle would be 0.75 meters, but then to that, we would also have to add the span of 3 meters because we're doing it from point A. So it'd be half of its span plus the 3 meters. So for the location of the first one, we said that it was going to be half of the span, so 1.5 meters over 2. For the location of the second one, we said also half of its span. And then for the location of the third section, we said that it was going to be the 1.5 meters over 2 plus the 3 meters of the previous section. So this should give us 0.75 meters. Sorry. This should give us 1.5 meters. And then this should give us 4.75 meters, right? 3 meters? No, I'm so sorry. I don't know why I wrote down 4. 3.75 meters. Oh, There we go. So now that we determined the location and the force for each of these individual loadings, now to find that resultant force, what we're going to do is we're simply just going to add all of these three forces to determine that resultant force. So F of R is equal to R1 plus R2 plus R3, which is equal to 9 point plus 27 plus 4.5 kilonewtons, giving you a total of 40.5 kilonewtons. And we know that that loading is going to be acting downwards. So with that, we are done determining the magnitude of that resultant force. But now for the next thing, we have to determine where that resultant force is located from point A. So what I'm going to do now is I'm simply going to be drawing where each of these individual forces are. So for x1, it's 0.75 meters away from point A. So that's going to be somewhere around here. We said that the other one was going to be about here. Remember, we said mid-span, and the other one is about here, right? This is R1, this is R2, and this is R3. So now to determine the location of that resultant force, what we're going to do is we're going to be first pretending like we're going to be taking the sum of the moments acting at point A. So remember, counterclockwise is positive. The sum of the moments about point A is equal to, we know that the moments are equal to the force times the distance, correct? So we know that since there's more loading, I guess you could say on this side, that resultant force is going to be on the right side of point A rather than being on the left side of point A. So we know that the resultant force is somewhere on this side, right? Since we know it's going to be on the right side, we know that's going to be creating a clockwise moment, meaning that's going to be creating a negative moment. So we could write that down. It's going to be a negative moment. And then we remember, we said that moment is equal to force times the distance. Our force is our resultant force, and our distance is, well, the location of where it is from point A. So we have this. So from here, what I'm going to be doing is I'm going to be simplifying this term down even more. So basically, in other words, our moment, besides it being the force times the location of that resultant force, it's also equal to each of these forces times their distance. So we know that R sub 1 is on the left side, so it's going to be creating that counterclockwise moment, so that's going to be a positive moment. So we have a positive moment of the force times the distance. From there we have R2, which we know it's on the right side, so negative moment, and R3 is also on the right side, so another negative moment. So from there we have minus R2 times X2 minus R3 times X3. So now that we wrote this out, as you could see, we said that this is equal to this, right? So now what we're going to do is we're going to be rewriting this in terms where the location is going to be left on one side, since that's what we're trying to figure out. So we said that this is equal to this. So now we're going to be rewriting this in terms of just the location of the resultant force, which should end up giving you something like the location of the resultant force is equal to R1 times X1 minus R2 times X2 minus R3 times X3 all over our negative resultant force. I also missed the step. Sorry. The signs of each of these are going to be the opposite. Okay, now we could plug in our information. So we know that the location of the resultant force is equal to negative 9 kilonewtons times 0.75 meters plus 27 kilonewtons times 1.5 meters plus 4.5 kilonewtons times 3.75 meters all over our resultant force of 40.5 kilonewtons. So now we're going to plug that into our calculator real quick. So that should give us a total of, that should give us that the location of the resultant force is 1.25 meters to the right of A. And just like that, we are done with example 4-11. So once again, it was asking us to determine the resultant force and to specify where it is on the beam. So since we had three different constant loadings, what we did is we found the concentrated force of each of those loadings. From there, we took the locations of each of them exactly from also point A. And then from there, we summed up all the forces to determine our magnitude of our resultant force. Then from there, what we did is we set up we set up we set up the equation taking the resultant, the moment about point A, and then from there, what we did is we rewrote it. And then since these two were equal to each other, we just rewrote that to be able to determine the location of our resultant force. Then we simply plugged in all of our information and ended up getting a location of 1.25 meters to the right of point A. Please feel free to like this video and also subscribe to our channel if you guys would like to see more videos like this one.